Okay, so lecture number 6. If you've been paying attention to the schedule at all, you may have realized that the topic of this lecture changed. It used to be on hash functions and hash tables, but I always felt that that lecture was a little bit dry and not super interesting, and probably things that people have heard before in other classes. So what I wanted to do was go into a little bit more detail about grid space representations, because they are so useful. However, it's not immediately obvious why that is, or how you could take a problem like in a video game or in robotics or the real world and then translate that to a problem that's in a grid space. And so that's what this lecture is going to be about, is about grids in general. And at the end, I'll talk a little bit about another type of algorithm called a vector field. I've never done this lecture in this class before, but I think it'll be fun because it's just a little more interesting than the previous lecture that I used to have in this slot. And just as a quick note to start off, in this lecture I'm going to be mentioning games a lot, and that's because my work is in games and AI, and so I use games all the time. At any time that I say, hey, this is what we do in games, this could also be any problem in robotics or problems in the real world as well. It's just that I'd like to say games because that's what I work in. And if you remember from the first lecture, I think pretty much everything can be represented as a game if you want to, right? So, okay. So space representation, we talked a little bit about this in the lecture when we talked about, remember that Newfoundland problem? How we break up that problem into space and action representation. But I'm going to go into a little bit more detail. So how we choose to represent the game or real-world space for problems like pathfinding, that's an important consideration. Space and action representations are important decisions, as we talked about before, and they're linked, right? Because the type of action that we can do is often directly related to the type of space that we've chosen to represent our problem. And so which representation to choose is based on a bunch of factors from the problem description that we've seen before. If we look back at Newfoundland, do I represent that as just, towns in a graph or 1 square meter, etc.? So the choice of space representation in the pathfinding algorithm will determine the movement actions that can be performed, and also the types of algorithms that we can actually apply to solve that problem. And so some more considerations when it comes to representing the space for a problem. Localization. So how do you find where you are in the representation? That's important. I'll give an example of that for grids in a little bit. Generation. How do we actually generate the representation? So how do we take it from like an English problem description to an actual thing that we can store in a computer and apply an algorithm to? Dynamic changes. So how do we handle dynamic changes to the environment, right? So if you are a robotic vacuum walking around, you might have a cat walk in front of you, or a person. How do you just try and keep going along that path? So how are you able to change your representation if something happens dynamically? How are the actions computed and represented? That's going to be an issue. And also, how much memory and time are going to be required to compute the paths, right? Because if we have this like really arbitrarily small precision environment and the paths are really, really precise down to the millimeter, then probably that path is going to take a lot longer to generate and a lot more memory to store than if it was a 1 meter or 1 kilometer, etc. So let's look at a couple of different space representations that we could employ in different environments. So the first one, I'm just calling this arbitrary precision, right? So we have things in the real world or in a game, they could be stored at some arbitrary real valued floating point precision. So my cup here is at 3 meters and 21 centimeters and 2 millimeters, etc. So this would be, you can store pretty much anything as this representation. We've already talked a little bit about grid structures, but we'll go into more details about this throughout the rest of the lecture. But this is where we're going to chop things up into a really nicely digestible, easy to apply algorithms to this domain. We could also have a graph or node representation of this space. So maybe there are only a few specific places in this environment where we could actually walk, right? Or we could navigate to. And so why worry about all the other space in the environment if we're only able to traverse along these nodes? That would make the problem much, much easier if we can only go to 20 or 30 different locations rather than possibly millions. Another thing that's popular is to chop up the region into what are called convex polygons, okay? So a convex polygon, one definition of a convex polygon is that anywhere inside a convex polygon is visible to any other place inside that convex polygon. And so, for example, here we have a rectangle. A rectangle is a convex polygon. This one is also a convex polygon. So what that means for pathfinding is that if we know we are inside a convex polygon, then that means there is a straight line that exists between any point in that polygon to any other point within that polygon. So that would be really beneficial for pathfinding, right? And so convex polygon representations, then what you would do is you would take this and turn this into a sort of graph. So for example, if I was trying to get from up here to over here, then I could first do pathfinding at the polygonal level. So I could go from this polygon to this one, to this one, to this one, and then I know that once I get to my final destination polygon, well, I can just walk in a straight line. So that's another type of representation. And then we could go even one step further and turn all of those polygons into triangles. And so triangular representations are good because lots of algorithms work on triangulation-based shapes. In this lecture, I'm going to give some examples of a game called StarCraft. Has anyone ever heard of StarCraft? A couple of people. So it's a real-time strategy game where you're sort of the general of an army looking down at all your units, and you like issue commands to possibly hundreds of different units. And the reason I'm giving this example is because I'm very familiar with it. And StarCraft 1, which we'll see in a little bit, used a grid-based representation, but StarCraft 2 moved to a triangular representation. I know it's a little bit hard to see here because of the light coming in through the windows, but the space is broken down into all of these polygons, and then those polygons are broken down into triangles, and then the pathfinding engine in this game tries to pathfind between the centers of those triangles. And so it's a bit more of an advanced representation. We won't be going into too many details about that. If you are working with modern game engines, then you will see what's called a navigation mesh, or a nav mesh. And so this is a screen capture from an old version of the game engine called Unity. And here, the person using this game engine is editing the navigation mesh. And so what you can do in a modern game engine, it can do this thing where, okay, if you draw a grid-based navigation mesh on top of your environment, then it has a pathfinding algorithm that works on that grid-based navigation mesh. And then as long as you put it in your environment, it will do the pathfinding for you. But of course, in this class, we're actually doing the pathfinding algorithm, right? So underneath, somewhere inside this game engine is probably something like the A-star search algorithm that's doing the pathfinding for you. So this lecture is all about grids. So let's talk about why grids are cool and what they are. So grids are 2D structures that divide the world into equally sized cells. Now, not every single grid you'll ever see is going to be equally sized, but 99.99% of them are going to be, right? They don't always have to be square, but they are typically equally sized. So if they're all triangles, or they're all squares, or they're all rectangles, or they're all hexagons, typically they're going to be equally sized. They're the simplest possible method to implement many, many different search algorithms on, and a bunch of other types of algorithms. And essentially they're used to represent two-dimensional surfaces. Those surfaces, as we'll see, typically don't have to be completely flat, but you can't have like things on top of other things if you want to just represent them as a 2D grid. So grids do have a limitation that if there's like complex 3D structure to your environment, then you probably can't just use a simple grid. Or you would have to use multiple grids, one for each level of that 3D structure. So they're used in many, many different games. Just, I mean, a couple of examples here. You can tell my age by the games that I'm referencing here, but things like the Warcraft series, StarCraft, Dragon Age, pretty much every single game that exists uses some form of either grid representation or triangular representation for its pathfinding. And what we're doing when we use a grid is we use a grid to abstract some more complex space into a space that's simpler so we can perform tasks on this new space, right? So ideally, we would be able to run our algorithm or whatever system on the actual environment space. But it turns out that oftentimes that's just far too complex. And so we reduce things to a grid, and then we run the algorithm on that grid. So the idea is to run the algorithm on the grid cell coordinates rather than the actual coordinates in the game world or in the robot simulation or whatever. And the good thing about grids is that they can be implemented by a 2D array or a vector internally. So the vector here meaning just a dynamically sized array in whatever programming language. So some programming languages may say, like for example, in JavaScript, we don't use a vector because the arrays in JavaScript can be resized, right? So we can add things to arrays in JavaScript. But if you're working with something like C++ or Java, you would have an actual vector and an array. So an array would be a statically sized array, and a vector would essentially be a dynamically sized array that we can add things to and remove things from. And it's used for many, many, many different types of tasks. And so I'll just show a couple here. So this is a screenshot from the game StarCraft, and so a lot of my research has to do with this game. I know it's a very old game, but it has a lot of interesting problems that you can solve within it. And so, for example, something that you can do in this game is build like a colony or a town or a base. And so the way that you will build things in this area is based on a grid. So some of these grid cells you will be able to place buildings on, and some of the grid cells you will not be able to place buildings on. Also, where you can navigate to on this map is also decided on by a grid cell. And it turns out that some games and some environments are going to have different hierarchies and sizes for these grids. So we're not saying that, okay, this is one problem, it's going to have just one grid. There are actually multiple different grids within this game that all do different things. So just as an example, from this game here, StarCraft, there are three different types of grids that are used in the game engine for this game. The first is at the pixel level. So we all know what a pixel is, right? Like it's just one little dot that's drawn on the screen. And so units in the game can actually move at a pixel level precision. So I could take my unit and move it over by 1 pixel or 37 pixels or however many pixels that I want. So the units in the game can have an arbitrary precision to their actual position within the game. Then we move up a little bit in terms of abstraction, and now we have the walk tile resolution. So tiles here are like the grid cells on the map. So if we take all the pixels in the map, if we form a grid out of 8 by 8 pixels, then what the game stores internally is this Boolean 2D array, which says, okay, I can either walk at this location or I can't walk at that location. So you can't walk over these false tiles and you can walk over these true tiles. And this is the resolution of the pathfinding engine for this game. So at 8 by 8 pixel resolution. But when you want to build in the game, the buildings are pretty big in comparison to the units, and so the buildings don't use the same resolution as walking, they use a larger grid. And you've probably seen this in games before, like SimCity or City Skylines or other building type games. You know, you can move around at a very fine level resolution, but you can only place large structures at a very coarse resolution. And so that's what this is doing. It's saying that, you know, certain tasks require a certain resolution, and so we will have different grids to represent those resolutions. This is an RPG called Dragon Age. Has anyone ever played or heard of the Dragon Age games? Okay, nobody. I think they're still being made, but there's like, I don't know, there's like 5 or 6 games in the series. And here we can see a sort of debug view of the world. And this world is like, it's a complex 3D world, but the base level navigation for the game is done based on this grid. And so here we can see the grid are these like little, the grid boundaries or the grid squares here are these little green dots, and the grid is spaced out over the entire environment. And so these navigation meshes can be an arbitrary graph structure, but they could also be a grid structure. Excuse me. Okay, so we have some world or some game or some simulation, and the thing is, our entities in that environment can live at like arbitrary precision values, right? Like if I wanted to apply a grid algorithm to like real pathfinding, actually, it's funny, we actually have a grid on the floor. There are square tiles on the floor, right? So I'm standing at this like arbitrary millimeter precision in the real world, but my grid, the abstraction we're trying to do is that we're going to take that and we're going to move you to a more abstract position in this grid space. So what we have to do is we have to translate from this game world or from the real world to a cell position in the grid world. And then later on, probably translate back from that cell position in the grid world to a position in the real world. There's a bunch of different ways that you could do that. Probably the easiest way, if we just look at this example over here, is, okay, my entity is in here. You can kind of see which cell that this entity is in, right? So we would say that this entity here that is entirely contained within this cell is at this cell. But in terms of math, how would we do that? We could just truncate the value to the nearest integer and then divide it by the width of the cell. So for example, if we have a position of an entity at like 23.6 in the x direction and 44 in the y direction, if we have chosen to make our grid cell sizes 10 by 10, then we can just take those and divide them by 10 and then round it off. So for example, 23.6 divided by 10, that would just become 2. 44 divided by 10 would just become 4. And so that's how we would translate from our grid position, or from our real world position into our grid position. There are lots of games and lots of environments that are actually played on grids. Like, I'm sure we've all played a board game like chess or checkers. Those are played on grids. But there are other video games as well. And so if we happen to have an environment that is already on a grid, then that's great because we don't really need to perform any of this translation. But the thing is, the grids aren't always square. So here, for example, I have a bigger screenshot of that in a second. And so these grid games need no like translation from one grid to another. We can just work directly in the grid structure that those have. And the game space and actions are going to be defined by that grid. So for example, okay, who's played Civilization or any type of Civilization game? Few people. So Civilization is played on a grid, but that grid is hexagonal. Okay, and it turns out, even though you might say, oh, these grids have 6 sizes, it turns out if you just rotate it like up here, you can just call this position 0, 0, 1, 0, 2, 0, 3, 0, 4, 0. And so you can actually, even though it's a hexagon, you can still represent it as a normal 2D array with those x and y values. And so grids aren't always square. Here's an interesting pathfinding example that I saw once where this world is actually made of triangles. And similarly, even though these aren't square, you could still say, okay, this is position 0, 0, 1, 0, 2, 0, 3, 0. And so you can easily map these grid coordinates into a standard square grid coordinates. And typically, if you do have any grid that's made of any regularly sized polygon, then you'll be able to translate the grid coordinates of that grid into a square or rectangular grid. Okay. It's not always the case that we want to do pathfinding. Sometimes there are other things that we would want to be able to do in an environment. And so a task location grid is another type of grid that you could sort of overlay onto an environment if you want to. And so this is used to determine which tiles or which cells of the grid that we can perform desired tasks on. So for example, where can we walk? Where can we build? If we're a robot, it's maybe where can we clean? So I have one of these robot vacuums at home, and it's really cool. It maps out, maybe I should have put a screenshot up here, but it maps out your whole house, right? And for example, I noticed once that the robot actually got stuck on this really fuzzy rug that we have. And so you can draw a grid over that map and you can say, okay, in these grid cells, the robot's not allowed to go there, right? So this is an actual real world problem that also uses a grid. And so what we can do is, let's say initially we have a grid that says I can do anything wherever I want, right? And then what we're going to do is we're going to say, okay, there are some places that I can't do some of these tasks. And so what we would do is, like, let's say over here, for example, that we were talking about pathfinding, and we do have some obstacles within that environment that we won't be able to pass through, right? So over here, maybe this is going to be a walkability grid. So the task is going to be walking, and we're going to say, okay, which places in this environment can I walk on, and which ones can't I walk on? So over here, what we're doing is we're saying, okay, well, we have to somehow translate those actions from the real world into this grid space. And so what we do is we just take every object that we see in the real world space, which could have arbitrary precision, and then we say, okay, which grid cells does this overlap? And then we would mark those grid cells as not being able to be traversed, right? So for our assignment, this was really easy because it's just a literal grid world where some tiles are blue and some tiles are green, etc. But how would we actually take a real world problem and get it into that space? That's what we would do. We would take like the map of the environment and we would trace out that map, and wherever this border was, we would actually mark those grid cells as I can't walk there. So now what you can do, the reason why this is so good and the reason why we would want to use a grid, it's let's say we weren't using a grid and we wanted to be able to tell, okay, my object is at this location, can I walk there or not? Well, what I would have to do in that case is like loop over every single object that I have and possibly do some really complex math to say, does this point where I am lie inside of any of these arbitrarily shaped polygons? And there's some complex like linear algebra and stuff going on there. And so by creating this grid map, what we're doing is we now have a constant time check because we can just look up in this grid, hey, is this grid cell blocked or not, right? So that's really good. So we've taken this problem, which is a little bit complex, and we've reduced it into just a constant time check of whether or not I can do that thing at this location. And so that's really great, but the downside here, and this note at the end, in some games, we may be trading, like now we have a much faster data structure for doing this lookup, but we are trading some accuracy for that. Why? Because if we were actually pathfinding in this environment, it's possible that we could actually walk in this area, right? But now the grid is saying, because the grid is a more abstract, more coarsely defined area, that I cannot walk in that area. Why? Because some object touches it somewhere, right? So that's the trade-off here. We take this arbitrary geometry, like really high precision geometry from a real problem, we translate it into a grid. So now our algorithms run faster, and our all these checks and lookups may now be in constant time where they weren't before, but the trade-off here is the accuracy, right? So how do we make it more accurate? Well, does anyone have an idea for how we could make this more accurate? Yep.
You split the cells into like smaller grids.
Yeah, so we just decrease the size of the grid cells, right? So we can keep going down to the pixel level if we wanted to. But the whole point of a grid is to be more abstract so our problem space is easier. So now this choice of how large is the grid, how many cells or how many tiles do we use, how many times do we divide it up, that's the issue, right? How fast do we want the algorithm to run versus how accurate do we want the results to be? There's always trade-offs in all of computer science, no matter what. So here's an example from StarCraft 2, and what this is a grid that defines where we can build things, okay? So I'm trying to place this building here, and what it's telling me right now in this game is that I can't place it here because this area is red. So this is called the command center. It's kind of the home base for the Terran faction in the game. And what I would like to be able to do is place it as close as possible to these resources, because I'm going to be gathering those resources, right? So if I want to gather the resources as efficiently as possible, I don't want to be having to walk like hundreds of meters back to the base to deliver these resources. So I want to place it as optimally as possible within this. And so the game has a grid here which says, okay, if it's red, that means I can't place it in that location. If it's yellow, it means I can build some things there, but I can't actually build my command center too close to the minerals. If it's green, then I can build things there. And so that's how this game does this building problem with a grid. Here's another game. It's a bit of an older game. It's called Warcraft 3. But in this game, the terrain isn't completely level, right? It's a bit wobbly. And you might say, okay, if there's a little bit of height in this game, how could we still use a grid? It turns out we can absolutely still use a grid. As long as none of those hills overlap other areas, we can still use grids to represent our space if we want to. We could have another grid that maybe records the height of a location or something like that, but the point being here for this example is even if it's not completely flat, we could still use a grid to represent that space. So here's a little example from the game. This is, it's a little bit hard to see here because it's not quite as dark as I want it to be. But this is the placement of buildings in the game. And so this is, again, this game, you're trying to like destroy the other player in the game. So one thing that you might want to do is build a sort of wall at the entrance to your base so the enemies can't come in. And so what you can do here is, if I can replay this, is this player is trying to find like the optimal placement for these buildings on this grid so that none of the grid cells, there's no gaps in this wall when they build it so that their opponent can't come in. And so that's how you build it. That's how the game, this is like a video from the actual interface of the game while you're building things. Okay. So in general, like we said before, filling the grid may involve computing polygon, edge line intersections with the grid lines. It might be a complex task, right? And we want to simplify things as much as we possibly can. But one of the really good cases in all of computer science is that if we can somehow represent our environment as axis-aligned rectangles. What axis-aligned means is that the rectangles in my grid space are aligned parallel and perpendicular with the rectangles in my object space. That would be great. Why? Because then I wouldn't have to do any of these complex operations at all. So I'll just give an example of that. So let's say we have an obstacle in our environment that's just a rectangle. And we would want to be able to mark, for example, if this is a big rock, right? So this is a big rock that we can't walk through or we can't build on, etc. And we want to be able to mark all the grid cells underneath this as false because we can no longer walk there. So you may say, okay, what am I going to have to do? Am I going to have to take this line and then loop over my whole grid and say which grid cells do this intersect with? No, we can, if the rectangles are aligned horizontally and vertically with each other, we can do a big shortcut for this. So let's look at that shortcut. Oops, I went backwards instead of forwards. So first what we're going to do is we're going to take the top left corner of this rectangle. If we take the top left corner of this rectangle, we can very easily compute which grid cell that overlaps with, right? Because we already showed how to find that grid cell location. Then what we do is we find the bottom right grid cell of this rectangle. And then all we have to do is we can just say, okay, because I know that these are straight lines, all I need to do is loop from the top left grid cell over the X's and the Y's and then mark all of these as blocked. Okay, so hopefully you can see how easy that is now, right? So if we can somehow represent our actual space in this way, where our obstacles or our agents or whatever are axis-aligned rectangles with the grid, then all of these calculations become very, very fast and very, very efficient. So that's just if you are going to be tackling one of these problems, if you can align things this way, it will make all of your computations very, very, very fast. You don't even need to do a single line segment intersection. It's just a little bit of division, which is great. So once we have our task grid, for example, if we're talking about movement, so the grid, now we can say, okay, so for example, over here, the blue tiles may be where I can walk, and these no walk tiles are in gray here. So this is very similar to our assignment. And so with grids, if we're talking about a problem like movement, the good thing about grids is that movement and actions typically only involve adjacent cells. And if we were talking about a more arbitrary precision environment, then our movements might be far more complex. You may be walking in a straight line somewhere, over an obstacle, around a curve, etc. But one of the other good things about grids is we're typically only talking about adjacent cells. Now you could have, other things where there's teleportation or things like this, but we'll just ignore that those exist. And so in grids typically, and we've seen this already, For assignment 1, we have legal actions of up, down, left, and right. In assignment 2, we will have this case down here where you can move up, down, left, and right, and diagonal for assignment 2. So that's a good thing. Another good thing about grids is that the action spaces are typically restricted to only adjacent cells within the grid. So for our assignment 1, this is what we have. This is our 4-directional shortest path, and then in assignment 2, we'll be talking about 8-directional. And I have a whole lecture set up for assignment 2, so I won't get into that too much. I put these, we already know about grid cells and actions, so I'll just skip a couple of those slides. But a really cool thing is that grids can also be used in environments that are not strictly flat areas. So this is a game, it's called Trudy's Mechanicals, and this game is essentially a grid, but each grid cell is at a different height. And so part of the fun of this game is trying to pathfind between places on this grid. So in this grid, you can move to adjacent cells, but you can also jump, I believe it's either 1 or 2 tiles upward as well. So even if the environment is not strictly flat, as long as no tiles in the environment overlap other tiles in the environment, you can still use grids to represent things. So what we've seen so far is that one of the most common things that we're going to be doing with grids is pathfinding. And so fewer positions and actions to consider in an algorithm than the native, sorry, that's worded really badly. But in a grid, we have far fewer states and actions to consider than like the real world. So one thing you might be asking, how can we take a real problem and actually apply grid world algorithms to it? And if you've ever seen a video game that does this poorly, you might be thinking, okay, I've seen a video game where like characters are walking around and you see them like walk in a straight line and then turn 90 degrees and walk in another straight line and then maybe turn 45 degrees. And that looks really bad. And that's not what we want in our games, for our robots, for our simulations, whatever. So luckily, we can do something that makes it so that that doesn't always happen. It's not always this really robotic movement. So first, we're going to take our game world or our real world. My camera may be covering up this in the video, but this just says game world. And in our game world, we have a completely arbitrary precision. Okay, so we have maybe a starting location up here and a goal location down there. So once we have our locations and our obstacles and everything set up in our real environment, then we can choose what our goal is. Is our goal to pathfind from here to here? Is it to capture some base? Whatever that is, we define our goal. Then what we do is we overlay some precision grid based on that environment, right? So obviously, I've sort of cherry-picked this to be really matching this environment. So here, this grid that I've overlaid nicely encapsulates the environment. I could have had a larger, more coarse grid. So I could have a grid where this whole object, maybe, let me go back here. I think I can use a pencil, right? So I could have a grid that where my grid cells are this big. And it just has, okay, this is one cell where there's an obstacle in it. But I've chosen to go with this size of grid. Then what we do is we do what we did a few slides ago, where we say, okay, this thing in the middle here, that's going to be an obstacle. So I want to mark these grid cells as non-traversable. So that's what I'm going to do here. Now we can see sort of how this aligns up with the assignment. Then we have our grid values that are set. And so for example here, we might be able to pathfind or walk around on the blue tiles, but not on the green tiles. Then I take these arbitrary precision starting and goal locations, and I translate those to the grid cell locations that I'm worried about for the grid pathfinding problem. And so here, that would be the starting cell here and the goal cell here. Then I would choose my actions based on this, this grid representation. So just for simplicity, we're going to choose up, down, left, and right for our actions in this space. Then, as we know how we can do that now, we run our pathfinding algorithm to find a path in this space. And starting at the next slide is where we see something that we haven't seen yet, and it's even though we have a path that looks like this in the grid representation, what we can do is we can then refine that path in the actual real world or game or whatever. So let's take this path, and how would we actually take this path from a game world or from a grid world and follow this path in, let's say we have a robot or a person walking around, etc. One of the ways that we can do that is to generate what I'm going to call waypoints. So for every action that we had in the path, we're going to take waypoints associated with each of those actions. And then if we have an actual robot following these, we can say, okay, I'm going to start at the start and then go to the first waypoint, then go to the second waypoint, then go to the third waypoint, the fourth waypoint, all the way until we reach the goal. And because of the way that we've done the pathfinding, we know that the way is always going to be clear to go from one waypoint to the next waypoint, because that was a legal action in our space. Then what we can do is we can take this, and now that the problem is sort of solved, right, we have the path, we can get rid of the grid at this point. So we have our solution that was in the grid space, and now we translate it back into the game world or the real world or whatever that is. And now what we could do is, let's say, okay, it is going to look quite robotic if I try and follow this path, right? Because I'm just going to go down and like reach this L shape and then turn 90 degrees and then keep moving straight. That won't look very good. So if this was our path that we want to follow in the real world, we can then do something that we call path refinement. And so refining a path means taking a path that was generated in this other more abstract space and making it look just a little bit nicer for the path in the real world. So for example here, we might be able to process this and say, okay, instead of going from one waypoint to the next waypoint to the next waypoint to the next waypoint, how about instead I try and go from one waypoint to the furthest waypoint that I can see that's not blocked by anything, right? So let's have a look at this here. I might say, okay, I can actually go directly from this waypoint to this waypoint because there's nothing blocking me from doing that. And so that's what this does. This step maybe throws away some of those waypoints so that now we have an even better path that we could follow in the real world or in the game that has this arbitrary movement. And then maybe we even refine it even more so we could fit this to a curve or do some other mathematics on it to make it much better. So that's how we could take like this problem in the real world, translate it to a grid space, run the algorithm in the grid space, then translate that path back to the real world, and then do a little bit of refining on that path to get something that looks like this. And this doesn't look like it was done in a grid space whatsoever, right? This looks like it was actually done on the real coordinates. And that's what happens in pretty much every single video game you've ever played, is that there's some grids, there's some representation, possibly, you know, just arbitrary floating point representation of all the entities in the game. It translates it either into a grid space or a triangulation space. It does the pathfinding in that simpler space, and then it, once the path is found in that space, it refines the path to actually look better in the real world. Okay, just gonna take another drink. So some advantages of grids. First, they're extremely easy to implement. It's just a 2D array or a 2D vector, etc. They're easy to visualize. It's intuitive how you would use them. The math around it is very simple. They're very quick to modify for dynamic changes, right? So if I go back here to my grid, if all of a sudden there was a new obstacle that appeared here, I could just add it. I could just mark that grid cell. Very, very easy to implement dynamic changes in that array. Arrays are very cache friendly, which means that I'm not going to go too much into cache coherency and stuff here, but essentially, once you get down to really low level optimizations in pathfinding, of course, we're not doing that in this course because we're using JavaScript. It turns out that like all the math that you're doing is actually secondary to just looking up the values in RAM. And it turns out that if you store things in arrays in nice contiguous memory, that becomes very, very fast. And we want to do that wherever possible. It's easy to specify and understand the actions. So if we had an arbitrary precision space, how would we define the actions? Could we walk 1 meter in a direction or 2 centimeters or whatever? But in a grid cell, it's really easy. We just move up, down, left, or right, maybe 8 directions. Any graph search algorithm can also work on a grid, because a grid is just a graph. It's just a graph with up, down, left, and right as the edges instead of arbitrary edges. And there are also some algorithms that are super efficient that only work on grids and don't work on arbitrary graphs. And I'll show you one of those in a little bit. However, one of the disadvantages of grids is this problem of localization, right? So for example, in this case, if we wanted to move from here to here, our grid-based pathfinding algorithm might make us move to like the center of this cell, and then we would see this little like refinement here at the end. And so however big you make your grid cells, you're essentially throwing away that much precision, right? Because we could be at the very corner of one of those cells and we have that level of inaccuracy in our environment. And so maybe we want to do this versus we want to do this. We would have to work out how we want to do those things. So grid abstractions may lose precision. They oftentimes do. Since the game or real world entities have real valued precision, and now we're translating that to a grid, we're never going to have full precision there, no matter how fine-grained we make the grid. Complex geometry is not well captured in a grid. Rectangles don't encapsulate all cells very well, or all shapes very well, and so that's just another loss of precision. And grid memory usage can be very, very high, and I'll show you why that is in a second. Grids are very inefficient for sparse spaces. Sparse spaces are where we have a very, very large space, but only a few of those spaces are actually walkable. And so here's an example from Dragon Age. This is an actual map from the game. It's called Orzammar. There are 96,600 walkable tiles in this grid. But one of the constraints of a grid is that it is a two-dimensional array. So we can think of here making this gigantic 2D array that we're storing like these hundreds of thousands of cells in, but we're really only using maybe 10 to 20% of those cells for the actual pathfinding. So this is one of the problems with grids, is that if you have sparse geometry, then grids are very inefficient because you have to store the entire bounding rectangle of that grid. Here is another example from Dragon Age Origins, where we have this environment that the environment itself is quite big, but the walkable space within that environment is not that big. Also, not only sparse spaces, but just, big spaces. And so if we want this is an example of some StarCraft maps where we have 1024 by 1024 sized walkability grid. 1,000 times 1,000, that's 1,000,000. And so now our grid has 1,000,000 cells in it, right? And so if we think about doing pathfinding on a grid, even though it is a sparser representation, searching over 1,000,000 things is not instantaneous, right? It still takes quite a bit of time. So just keep in mind, whenever you choose to use a grid for a representation, even though you can do it, you may not always want to do it. And these are the things that we said that we had to consider at the beginning. However, grids do take a lot of memory, and sparse grids may only hold potentially few values. And because of that, I have already said all this. Yeah, so I didn't realize I had a slide that did that. So if possible, we want to avoid these really large sparse grids. But there are some things that people have done there out in academia and in some games to try and solve this problem, where maybe we could have a hierarchy of grids, for example. So we're going to break our grid, like I think you said before, break our grid down into smaller grids, right? So here we have an example where we take this 16 by 16 grid and we break it down into a 4 by 4 grid. And now maybe what we could do is do the pathfinding first at this really coarse 4 by 4 level. And then once we have that path, then we go only to those cells in the previous grid and do the actual fine-grained pathfinding in. Some other people, this is from another paper I saw, where they take the intersections between these cells and then they form a graph out of those. So if you can take a grid that's really sparse and then you form a graph out of it, then you could do the pathfinding on the graph, and then translate those actions back into the grid. So just because I said, sparse grids are inefficient doesn't mean there aren't a lot of really smart people thinking about this problem and coming up with some solutions for them. Okay, next we're going to talk about vector fields. Vector fields are really cool. I've implemented this as an assignment for a different course that I no longer teach, and I'll show you a demo of that once I'm done with the slides. So in mathematics and physics and chemistry and a bunch of other places, a vector field is an assignment of a vector to each point in space. And so this is a vector from physics, meaning like it has a start and an endpoint, not a computer science vector that stores values. So from now on, wherever you see vector, I'm talking essentially like an arrow, right? A vector, it has a length and a magnitude, a direction. These are used in a bunch of different places. They're used in vector calculus, if you've ever done that course, for differential equations in physics, etc. And so in game programming, or what we're going to show, essentially we're taking our grid and we're putting a little line in each cell of the grid. And where that line points is going to represent, hey, we should do some action if we're at this cell in the grid. And so this vector denotes the desired action or direction of movement from that cell. There are lots of different vector fields in different parts of science. I'm sure you've all seen experiments with magnetism where they like lay a magnet down on some like iron filings, and the iron filings have these like directions, or the Earth's magnetic poles. They all form a vector grid. However, this vector grid is in like, this real valued actual space of the universe, not in a grid that we have defined. So here's just an example of what I'm talking about. We're going to have some grid space, and I'll explain what this does later. But we're going to have a grid space, and then in this grid, we're going to have directions pointing to where we should move, right? And I'll show you why that's going to be useful, but it's going to allow us to do things like this. This is a really cool example, and we'll get to this, of how you could have many, many agents trying to get to a single goal at the same time. And I'll show you an example from my assignment where there's like hundreds of thousands of agents doing pathfinding at the same time. And as you've seen, we probably don't want to be doing like the A-star search algorithm or breadth first search or IDDFS hundreds of thousands of times, right? So we'll see how we can do something like this really simply. So vector fields for games, sometimes they're called different things in different places. So they may be called flow fields, influence maps, vector maps. They're called a bunch of different things. They're very efficient structures for pathfinding in cases of many paths to a single goal. So one example of this, has anyone ever played or seen played like Diablo or Path of Exile, or these games where, you're walking around in an environment and there are like hundreds of enemies trying to get to you? Like a type of game like this. This is a case where vector fields are like really, really useful. So in any case where multiple entities or multiple NPCs need to go to a single location, I would consider using these. And they can be used to accomplish a bunch of different tasks, not just pathfinding, and I'll show you at the end how you can do different things with these. But first, in order to form a vector field, you first have to form what I am calling a distance map. So before we can compute the vector field, we need to compute a distance map, and a distance map is just a grid, and we're going to be able to do this using breadth first search. So each grid of the cell will store the four-directional, this is not four-dimensional, four-directional shortest path distance to a single goal, and we'll see how we can do that. So in practice, we're going to need one distance map per goal location, per destination. And then we can do that really easily if the environment is static. Okay, so here's how we're going to do a distance map. So this is just using breadth first search. So let's say that down here is maybe that's where the player in the game is, and there are hundreds of NPCs trying to get to that player. How do we get all the different paths just to that player for all those NPCs? That's just one possible case. So we're going to take the goal location, and we're going to start that at 0, because it has 0 distance to get to the goal, right? So this number that I'm showing here is going to be the number of actions that I have to take to get to that goal. So at the very start of the breadth first search, we're just going to say, hey, that's a 0, right? And so then we're going to expand that node. So this is the very same breadth first search that we've been doing. However, we're just recording one other bit of information, and that's the depth of the search. So I expand this node, and now I have a 1 at each of these locations in the grid. That means that from the destination, it took 1 action to get to those cell locations. Then, out from there, these all took 2 actions to get to. And here, just like our other BFS, we have a closed list, right? Because we don't want to go back to any of these things. So the closed list is just going to say, don't revisit these states. The open list, here we have this grid that's storing 2, then 3, then 4, etc. And what we're left with, once we've touched everything, is this data structure called a distance map. And what the distance map does is it records the number of actions that it took to get to the goal. Okay, so that's it. Can anyone tell me how I would know where to go to get to the goal from the distance map? Yep. Yeah, so that's a really great point. So over here, for example, if I was over here and I wanted to get to here, well, this is 15 actions from the goal, right? If I look up, this one is 16 actions from the goal. This one is 14 actions from the goal. So if at any point in this map, I just go in the direction of the lowest number, that means I'm getting closer and closer to the goal. That's it. So to compute the distance map, we just use breadth first search, as we saw before. Each child cell is given a distance value of the parent cell plus 1. That's it. Really easy. And every cell initially gets a distance of -1, right? Because it just essentially means at the very start, everything gets -1 and the goal gets a 0. And at the very end, if any cell still has a value of -1, it means that that cell cannot reach the goal, right? We'll get into this a bit more when we get to assignment 2. Okay, so from the distance map, it's really easy to construct the vector field. Each cell just gets assigned a vector pointing to the lowest valued neighbors. That's it. If I was at 15 and I saw 14, go towards the 14. Optionally, what you can do is if a cell points both left and up, we can replace it with a diagonal. What do I mean by that? Well, let's go back to this. So over here, this cell over here has 15. There is a 14 to the right, and there's a 14 down. And so I could point either down or to the right, or if I was allowed to move diagonally, I could also point diagonally down to this 13. It just depends on my action space. So that's what that's saying. And then, oh yeah, I already said this. And then, in order to move, just follow the vectors. That's it. So let's have a look at this illustrated example. Step 1, form the distance map. So I want to get, for example, from here to right here. So I did my breadth first search, I formed this distance map, and now all I need to do in order to get to the goal is go down decreasing in numbers, because if I get to 0, I'm at the goal. Step number 2, to form the actual vectors themselves, just point in the direction that you should go. And that's it. That's the whole algorithm. You already knew how to do this, you just had to get someone to show you the example. You all know how to do BFS, and you all know how to point, and so you can all write a vector field. So if I look at this example with the distance map showing all of these particles here at every time step, they're just moving in the direction of the lowest number. That's it, and this is what it looks like if you actually show the vector field. So that's pretty neat. I think it's just the same video again. The last 4 slides I took from this article, so I just wanted to give that article a citation. Some performance notes about breadth first search. And this, you can do this if you want for assignment 1 as well, and you can also do this for assignment 2. Implementing a breadth first search iteratively, as we've been talking about with our tree search and graph search algorithms, with a queue actually results in poor performance. Why? I'll show you in a second. Array-based queues need to left shift all elements to pop from the front, which can be very, very slow in practice. Who's been told that before? Okay, like 2 people? I'll show you why. This is an example of a dynamic vector or array in any programming language. This is how these are all implemented. So if I have a vector, and that vector has these letters D, R, I, V, E, and I want to delete this R, right? What actually happens? Well, in that array, we're not going to have a blank space anywhere in the array. So what has to happen is that when I erase this part of the vector, or this part of the array, all of these elements following that thing, they are all moved 1 to the left. So whenever you delete something from an array or you delete something from a vector in one of these dynamically sized vectors or arrays, every time you delete something, that is an order n operation. So you could, in the worst case, if you delete the first thing, have to move everything in the array to the left by 1. And when we're using a queue, which element are we deleting? We're deleting the first thing. So every single time we call array.shift, it's the worst possible case. And it's really, really, really slow. So how could we get away from that thing? Well, what we're going to do is we're going to do the thing that we often do in computer science, and we trade memory for speed. You can never have both, but we can trade a little bit of memory to solve this problem. So how can we avoid the actual deletion, but still get the things as a queue? Now, in the case of DFS, when you have a stack, you're just removing the last thing. So we don't care about that one, because we know if we're removing the last thing, there's nothing past the last thing that we have the shift. So if we're just popping from the end, this is an issue. This is not an issue. But if we're popping from the beginning, it is an issue. So we're going to simulate a queue using an array, but we're never actually going to delete anything from the queue. So what this is going to mean is that anything we ever put into this array is actually going to stay there. But we'll see how we do this. So to insert something into the queue, we're just going to add to the end of the array as normal. So insertions into this new data structure are going to be the exact same. However, instead of removing something from the front of the queue, instead, we're going to create an index that points to where we think the front should be. And I have an illustrated example of this, so just give me a sec. So instead of checking if the queue is empty, we check if the pointer is pointing to the end. And I'll show you, I think it's much easier to look at this illustrated example. So here is the simplest possible case where we have our queue, and this is at the start of our search where we just have the root node in our open list. So for example, let's say you have the open list implemented as an array. Whenever you add something to the array, you're adding to the end of the array. And whenever you remove something from the array, you're removing something from the beginning of the array. So in this case, we are never actually going to delete anything from the array. What's going to happen is this. Let's say my root node has 3 children, if I moved up, down, or right, or something like that. What I'm going to do is I'm going to add those 3 children to the array. But instead of deleting the first thing and then causing this huge shift that takes a lot of time, I am going to store the index of where the first thing in the array now is. You see this? So instead of actually deleting this, the array now, instead of having 3 elements, it actually has 4. But the front of the array is now element 1 instead of element 0. So in this case, I'm not actually removing stuff, I'm just increasing the pointer, okay? And then I have another pointer, which is pointing to the last element in the array. I say pointer, but this, if it's an array, it could just be an index, right? So this is index 1, and this is index 3. Now, let me expand this node. So if I was using a queue, I would take this node and remove it from the array, and then add its children, but I'm not actually removing it, I'm just increasing this index, right? So I'm keeping it in the array. So I don't have to take all these things and shift them every time I remove something. So now what happens is, the front of the array is right here, and the end of the array is right here. So the last thing we have to solve now is that if nothing in the array ever gets removed, how do I check if it's empty, right? Because the size is always going to be greater than 0. So how do I check if it's empty? Well, if I keep removing things, all I'm doing is increasing this pointer, and when the two pointers are the same, that's when it's empty. Okay? So in that way, I never have to do any of these linear time operations for deletes, which is really cool. So here what we're doing is we're trading memory, because we never actually remove anything from this array. Everything is still there, but we gain a lot of speed because we never actually have to do this really expensive deletion operation. So if you want to, you absolutely don't have to. If you want to have a chance at being the fastest assignment 1, you would have to do this, because this is really, really fast. But inside your open list class, all you would have to do is create 2 new indices. One is sort of the front index, and one is the back index. And then instead of calling shift, you would just increase the index. And in the function where you call front, instead of calling shift, you just return the element at that index. That's it. So you can do that if you want to. It's absolutely not necessary to get full marks, but it's the assignment, the solution does this to be really, really fast. So that's one way we can simulate a queue without actually removing anything. Another optimization, if we did want to do this sort of BFS with a closed list, right? So that closed list, if you implement that naively, that's just an array, and then you check the whole array. I've already been talking to some of you who've created like dictionaries or maps or whatever for your closed list, so that's great. You're thinking about that already. The interesting thing is, if we were to do a vector field, which we're not for assignment 1, but if we were to do that, we can use the distance map's initial values as a constant time closed list query in lieu of using a set or another dictionary or something. So initially, we're going to assign all of the cells a value of -1, and any state which has not been visited yet has a value of -1. To check if a state has already been seen by the BFS, check to see if its value is not -1. So in this case, instead of saying, oh, I have this other closed list data structure, I already have this distance map grid that I'm filling out, and if any value in that grid is not -1, it means it's in the closed list and I shouldn't visit it again. So that's a really cool way that you can use the same data for multiple different things. If you don't want to do that, like if you're not doing the vector search, then what you could do for assignment 1 as an optimization is have a separate Boolean grid where in this grid, you just say true or false, is this thing in the closed list? So the example of that, if you are if you're doing vector fields and you want a closed list, then anything that's not -1 is in the closed list. And otherwise, if you're just doing normal BFS like in assignment 1, you could make a secondary grid which just stores whether or not something is in the closed list. Now here I've drawn T's on the open list as well. That's because it's a little bit different for the vector field. But you know what I'm talking about. This concept should be pretty clear. The last thing I'll talk about is called an influence map. And influence maps are typically used to incorporate other logic that is not like just pathfinding. And influence maps are often used when it's difficult to come up with like a really good objective function that you want to try and minimize or maximize. Some examples might be, okay, I want to do some pathfinding, but I want to keep some distance from an enemy location or something like that. Or I want to be able to attack something but avoid cannons that the enemy might have. So it's a really simple addition to a vector field. So here's an influence map. The simplest possible case of an influence map would be, okay, when I construct my distance map for the vector field, I just don't assign any values to where this enemy might be. So for example, how would I do pathfinding but avoid this enemy? Well, I just don't assign a value to it, or I give it a value of infinity, and then I will never walk on that enemy tile. Okay. That's a pretty trivial example though. Let's say we have some game, and in the game, we're in a boat or something like that, and the boat might crash if it gets too close to the shore. So we want to do pathfinding but we want to keep a little bit of distance from this shore. But if we have to, we would still go next to the shore. So how could we do something like that? Well, this is where influence comes in. We would say, okay, I'm going to put 10 influence onto this cell. What that means is I would rather go 10 distance out of my way than to step on this tile. So then when I do my distance map, all of these values are much higher. And so here, if I was going toward the goal, I would see, okay, 16, 15, 26, I don't want to go there. And so I would go down here instead. And so this would keep some difference. I am influencing my decisions from going away from this area. If I wanted to go toward an area, I could have a negative influence in this case. Okay? Similarly down here, maybe there's like an enemy that has a cannon set up down here, and I don't want to ever go near that cannon, so I give it some gigantic influence number so that I will never go in there. But if there was absolutely no way of going up here, I would at least go through here. Okay? Here's an example of this in a game where we apply an influence map on this grid, and this blue guy now is seeing the negative influence by these enemies that they're trying to avoid. And there's no explicit pathfinding algorithm like A star saying, well, you have to maximize the distance from you to these enemies. No, it's just a grid of influence that's saying, I want to go to the least of these values. Okay? Similarly, there's one here where the blue ones are defenders, and the defenders are actually attracted to the influence of the attackers. And so here, I can make my blue guys chase the red guys by putting some negative influence there. And then the red ones don't want to be next to the defenders, so they are influenced by those defenders, and they'll actually run away when they see the blue. Okay, so hopefully you see how that works. And now I have a little demo that I want to show. This demo is actually written in C++, so this is something I wrote on my own outside of this class. But it just shows you how powerful vector maps can be. So this is an example. I'll try and zoom in a little bit. Okay, so here I have a yellow square that I can place in this environment. And here I can move these things around, and you can see how these are the obstacles that are in my grid space, right? So this rectangle I can move around. And now if I press P here, I can turn on some particles. So these particles are spawning at random places in the environment, and they want to get to this goal location. But they can't move on these blocked spaces, right? So you can see here how I'm actually losing precision here, right? Because of my obstacle being overlaid on this grid thinks that this area is not walkable, whereas these tiny particles could come down here if they wanted to. So that's one of the negative parts of using a grid, is that you do lose precision. But if I, for example, oh geez, sorry, I'm zoomed in and it's all over the place. If I did move this obstacle over, then all of a sudden these things could come down here. Down here, it's showing me the particle count. So there are 1,000 particles down here, and this is running in 9 microseconds, which is extremely fast. Let's increase the number of particles. This is running in 1 millisecond, and there are 262,000 particles, right? Because, why is that possible? Because it's all the same pathfinding grid. I don't have to rerun this algorithm for every single thing. Now, on the video, this actually destroys the bitrate of the video, so it might be really blurry. So let me, I got some help here. Half the number of particles, right? So yeah, I can change the particle size, and now it's almost like a physics simulation, right? So you can see here just the power of grids. This is crazy how cool this is, in my opinion anyway. Now we're starting to slow down. Now it's a full 3 milliseconds for 1 million particles, right? So grid-based algorithms can be incredibly efficient when used properly. And now the other thing I can do here is I can, where's my grid size? Increase number of grid cells. So this over here, this case, yeah,
where I lost a bunch of precision, one of the solutions to that would be to increase the number of grid cells. And by increasing the grid cells, now the amount of time it takes to compute is a little faster. But I think I can turn off the grid. Yeah, I can turn off the grid. The amount of time it takes to compute is longer, but I get more precision. And I can like increase new obstacles here, or introduce new obstacles, and all the particles run around it. And like if you were looking at this, you probably would not think that that was done with a grid-based algorithm, right? Because I've chosen those parameters properly and coded it efficiently enough that I think it's pretty cool. Now, we can't do that in JavaScript, unfortunately, and the course is not about like super optimizing things. I just really wanted to show you the power of grid representations when they are done properly.